Hello everyone, welcome back to Apache Kafka series. In this video, we are going to start looking into some of the features that came with Apache Kafka 3.0. More specifically, we are going to look into KRaft. If you are using Kafka 3.0 and above, you have the choice to either use a Zookeeper based controller or the KRaft or Kafka Raft based controller. And some of the reasons, like in previous versions of Kafka, that we can see, for example, Kafka cluster contains several broker nodes and an external quorum of Zookeeper nodes. As you can see from the here it says current, it means like the previous version of Kafka. Above here we have Zookeeper, and then we have a controller, then we have Kafka brokers. And the main thing here is that the Kafka controller, or the controller here, is the one responsible for getting all the metadata from Zookeeper and then pushing the metadata updates to the brokers, to the rest of the brokers. So though all the brokers also do communicate with Zookeeper, and in addition to that, external tools and utilities that are used for administrative purpose can also connect to Zookeeper and modify something without the consent of the controller. So if someone is to use other tools to modify some topic or some information instantly, this controller might not be aware of those informations. And it means like you are really not having an up-to-date metadata information to the rest of the brokers. And think of it, if you, for example, your controller restarts due to any reason, it has to read all the metadata from the Zookeeper and then send the metadata or pushes the metadata to the rest of the brokers. And so imagine like you are having too many brokers, or you are having a cluster with a lot of partitions, and when your controller restarts, it means that you are going to pull all those metadata, and this can slow down the restart of your controller. And by the way, also Zookeeper is its own distributed system, which means if you are dealing with Zookeeper, then you also have to learn some specific aspect of that Zookeeper in order to be able to manage it. So there's a bunch of information or bunch of things that are associated with Kafka. The Kafka made the Kafka community to think otherwise and try to propose a solution to the problem in which Kafka can be independent. You can see that with the new design, the controller is the boss here. The controller, instead of dealing with Zookeeper, it is the boss. It has the responsibility to manage the metadata. So with KRaft, the controller acts as quorum. Like here, instead of you having Zookeeper, you are having like controllers that runs in a different JVM. And these controllers, they act as quorum. And with this quorum, they manages the logs of metadata event instead of dealing with Zookeeper. So informations or metadata that are previously stored in Zookeeper, such as topics, partitions, in-sync replicas, and configurations, will now be stored in this Raft log. So you will have the information here. Unlike before that, the controller pull the information from Zookeeper and then pushes it to the rest of the brokers. In KRaft, the brokers pull metadata via the new metadata fetch API. And this means that a broker can, at its own will or at its own interest or whenever there is need, will pull the metadata information. It doesn't have to be pushed all the time. And the leader doesn't have to push this metadata. And also, depending on the state of the pooling, for example, if we come to the next slide, depending on the state of the pooling broker, it could either receive delta of the update, it means the broker will not receive huge update because it's almost close to the leader in terms of update, or dependent, the broker could also receive the whole updates, the whole metadata, if it falls too far behind the leader. So as you can see here, if a broker read cache metadata from the local file system during startup, when the broker restarts, the broker requests the changes since the last offset. So if the broker was too far behind, the controller sends a full snapshot, otherwise it sends deltas. So here you can see the broker writes the metadata to its own local cache. So next time it doesn't have to pull all the metadata again. And the broker can periodically ask for the update. This has eased a lot of things. And the remaining controllers will also replicate the data with the leader of the quorum, so that in case if any problem happens, let's say the leader is down, or due to network problem, or due to anything, then re-election will happen again. And in this case, whenever re-election happens, one of the controller or one of the controller in the quorum might be elected as the new leader. And because they all have the information, or they all have the metadata, loading the information again will not take too much time, unlike with the zookeeper approach. So Kafka brokers will all register themselves with the quorum. In the zookeeper version of the cluster, if a broker is not up to date with the metadata, it could still serve clients. And this leads to a lot of problems, like it can still serve the consumers and producers, though the controller could not receive metadata update, but it was able to serve the client request. For example, a producer using just AX1, which means like if any of the broker received the update, that is the partition leader received the update, it will consider the message as being sent, and might continue to produce to a leader that actually was not the leader anymore, because the leader has maybe restarted before and a new leader has been re-elected. But because with the zookeeper design, or with the zookeeper version of the design, the broker could still communicate with the client. So this is the problem here. And if a broker is not updated with the metadata in the new design, that is, the broker will be fenced, meaning that the broker will not serve any client, and consumer or producers will not be able to receive any information or read messages from the broker. This is with the next slides. If you can see, like here we have the offline, we have the stopping, we have the fence, we have the online. And here, in the case of offline, when the broker process is off state or is offline, it's either not running at all, that means it is down, or in the process of performing single node task, let's say maybe due to some issues, it has to restart, or it has to fetch some data from the local file system. So any of this, or it is initializing the JVM, and these things could lead to the broker being offline. So when this happens, and there is no update between the broker and the leader, the controller, the elected leader of the controller, then it will fence. And when the broker is in the fence state, it will not respond to any of the RPC calls from the client, that remote procedural calls. And the broker will be in the fence state when starting again. So normally whenever a broker restarts, or whenever a broker is starting, it fetches the update from the controller. And for that reason, when a broker is starting, it will also be in the fenced state. And it means it cannot serve the client. And data has to, or if the broker is trying to fetch the new metadata, still it cannot serve the client. It will also be in the fenced state. So it will re-enter fence state also if it can't contact the active controller. For example, we have the active controller, which is the leader, the elected leader. So if a broker also could not contact the leader, it will still enter into fence state so that it could not serve the client or the consumer and producers. And also when it fetches all the data, then it could be online again. And when a broker is online, it is ready to respond to requests from client. And also in some cases, if an admin is shutting down the controller, brokers also may enter into fence state. That is when the broker is trying to tell the elected leader that, okay, I'm going down. So here are all my information, the state, the metadata, the topic, the partitions that the controller is leader of. After sending all this information to the leader, then the leader will respond to the broker, okay, now everything is okay, you can go down or you can shut down. And then the broker will go ahead and just shut down. But if the broker or if the leader is not able to respond back to the broker, after some certain period of time, also the broker will shut down. So as you can see, the design in the KRaft base, it is a lot of things, and you are able to manage or to do everything with just your Kafka base. You don't have to deal with external source of information or external source of metadata management like we do with the Zookeeper. And we'll add all the links to this so that you can read more about it. And in the next video, we are going to look also into the practical implementation or application of this approach, how we can configure the KRaft brokers, and also look into how we can configure the cluster of the KRaft. So until then, thank you very much. See you in the next video.